see the PowerPoint. Let me show the PowerPoint. Please see, I highly recommend students to attend today's and tomorrow's exam recap because there's a lot. And this is the only way I can help you with the exam, okay? Right? Does everyone understand that? Everybody's good? Great. Glad. How's everyone? Everybody's good? And you can hear me well? Great. Today I will be having session only up to 6. I will not go fast. I will see how much I can finish up to 6 o'clock. We'll continue the next tomorrow at 10, our usual supplemental time. Okay? One more minute. We'll see you in a minute. You had any class before me? Was there any class?
Yeah, there was laboratory. So the last lab.
Oh, wow. That late? Oh my God.
Yeah, until 5.
People are working hard, huh? That's a long day. Okay, I think it's 5:15. Okay, so let me share my plan first of all. Look at this. This looks scary, right? But I'll make it simple. Know that you have 6 lectures. You have 3 primers and 1 CV. Please, as I always say, first finish your lectures. You got to focus on your lectures first. Then you have time, you go to CV. Then you have time, you go to primer if you don't understand. The focus should be lectures. There are 6 lectures and there are 18 questions, right? First, I want you to do is please get metabolism off your plate this weekend. Once you are done with metabolism, believe me, you have done almost 90% of your CP2. So please finish fatty acid synthesis, tag fatty acid oxidation, cholesterol, and lipoprotein. These are 4 major metabolism. Get them done this weekend and you will be fine for CP2. When I come back in the interactive session, I'm going to repeat everything, but I'm also going to do phospholipid and icosanoid, which I'm not doing now because phospholipids and icosanoids are not metabolism. They are topics and I need to introduce them in interactive session and you will be good. But these are metabolism. I don't want you to go wrong here. So let's start with fatty acid synthesis. And please know, yes, questions are evenly distributed, but you should understand metabolism is way more than phospholipids and icosanoid because phospholipids, icosanoids are straightforward. Though icosanoids are not so straightforward in Dr. Panini's lecture, but I'm going to introduce them in interactive session. So today, let's do only one thing. Can you hear me well? Just first of all, let's pat yourself too. I think you both DO and MS really did great in CP1. So be proud of yourself. Always think positive. See how can you go forward, right? So let's see how we can do CP2 too. Maybe go up higher. First, stick to your learning objective. You got to contrast fatty acid synthesis versus oxidation. So fatty acid synthesis, tell me which one is well-fed state, fatty acid synthesis or fatty acid oxidation, which is well-fed state pathway. Fatty acid synthesis, very good. Fatty acid synthesis goes into TAG synthesis. So TAG synthesis is also well-fed state. So now what is low insulin pathway? First, you got to compartmentalize these 2 pathways, fatty acid synthesis, fatty acid oxidation. Fatty acid synthesis goes into TAG synthesis. So both fatty acid and TAG synthesis are well-fed or low insulin pathway. Fatty acid and tag storage are well-fed or low insulin pathway? Well-fed pathway. What do you mean by well-fed? High insulin pathway, well-fed state. But now you got to understand what all these pathways require. Can synthesis happen without ATP? Can synthesis happen without ATP? No. So tell me, what would be the major requirement for fatty acid synthesis? Fatty acid synthesis go into tag synthesis, though I will tell you that carbs are killers. It's not that eating more fat in diet leads to fat. Also, eating more carbs in diet leads to tag stores. So carbs are the killers, right? So tell me, in fatty acid synthesis and leading to tag synthesis, so what all you need for fatty acid synthesis? Insulin, what else? High insulin, 100, well, very good. What else? You can unmute and answer to NADPH, because fatty acid synthesis, when you say fatty acid is made of carbon, hydrogen, yes, you need high insulin, you need NADPH. Are you missing one, which is very important? You need acetyl-CoA, because NADPH source of hydrogen, acetyl-CoA source of carbon. Are you missing something? ATP. Please know you cannot do any genesis without ATP. So if you think about fatty acid synthesis, you need high insulin, high ATP, high NADPH, and high acetyl-CoA. So let's see when we contrast it with fatty acid oxidation, what changes. But don't flip-flop that. And understand, please don't understand well-fed and low insulin at the same time. Just do well-fed state. Well-fed state in today's lecture is fatty acid synthesis going into tag synthesis. Low insulin state is then naturally, tell me the low insulin pathways today. If well-fed is fatty acid synthesis going into tag synthesis, what can be low insulin pathway? Fatty acid oxidation and yes, fatty acid oxidation. Anything else? That is, beta oxidation is fatty acid oxidation. That's the most common oxidation. One more thing, tag lipolysis. Tag lipolysis. Lipolysis of tag is also low insulin state. Yes, beta oxidation is fatty acid oxidation, because most common oxidation is beta oxidation or long chain. So let's do fatty acid synthesis, which is a well-fed state pathway, and let's see how carbs are killers. Is it cytosolic? Absolutely. That is why, do you need to bring acetyl-CoA in the cytosol to do fatty acid synthesis? So why am I talking about acetyl-CoA? What has acetyl-CoA to do with fatty acid synthesis? Is it a starting molecule for fatty acid synthesis? Is acetyl-CoA a starting? Yes. So yes, acetyl-CoA is the starting molecule for fatty acid synthesis. Acetyl-CoA, though, is formed in the mitochondria, but has to be available where? In the cytosol. That's why you should know compartmentalization. Also, why you should know compartmentalization, and I will compare and contrast oxidation, you will understand that. I hope you're following my pace. I don't want to be very slow too, but I don't want to be very fast. Are you following my pace? I just don't want to rush too much also. So you have the key points. Great. Main site also, please know some students get confused. Fatty acid synthesis and DNL, known as de novo lipogenesis, is the same. It's not different. Sometimes DNL is used. Main tissue, anyone? Liver, and there is mainly fatty acid synthesis. Sites and compartmentalization and state is important. So where is fatty acid synthesis, also known as DNL? Mammary gland is not a good answer. That's a minor site. I want major sites. Major first, liver and adipose tissue. Very good. Liver and adipose tissue. We will know the difference. Lactating, know the order. Liver, adipose tissue, then lactating mammary gland. Please know rate limiting enzyme for every pathway. We will do for fatty acid synthesis, fatty acid oxidation. We will do for tag synthesis and tag lipolysis. So are you aware of ACC, known as acetyl-CoA carboxylase? What do you form? You first form, what do you form by fatty acid synthesis? Do you form a fatty acid which is 16 carbon with no double bond? What kind of fatty acid you first form in your body? Do you form a 16 carbon fatty acid with no double bond? Yes, that's known as palmitic acid. Very good. This, you cannot do synthesis without ATP. But let's see why citrate is activator of fatty acid synthesis. So you got to concentrate on state, then you got to concentrate on compartmentalization. Site helps, but rate limiting enzyme and regulation don't flip-flop that. Now, why fatty liver? Because fatty acid synthesis goes into tag synthesis. And do you know that excess tag accumulation in the liver causes what? Excess tag accumulation in the liver causes, can you hear me? Excess tag accumulation in the liver causes, do you know that? Excess tag, fatty liver. That's why in alcoholics, you can see that. I will address clinical application too. So yes, acetyl-CoA is the starting molecule, but acetyl-CoA is not just starting molecule for fatty acid, it's also for cholesterol, and acetyl-CoA is the starting molecule not just for fatty acid, cholesterol, and can you fill it up because it's also in today's lecture. Steroid is not today's lecture, but that's a good answer. Ketone bodies. So acetyl-CoA is the starting molecule for fatty acid, cholesterol, as well as ketone body. Tell me which one of them is a low insulin pathway. Since acetyl-CoA is starting molecule for fatty acid, ketones, and cholesterol, ketone. All the genesis require ATP, and most genesis require insulin too. Which genesis do not require insulin, in fact? Which genesis does not require insulin? Lipogenesis require, in fact, gluconeogenesis is the correct answer, but in fact, which genesis does not require insulin? Fatty acid synthesis require insulin, cholesterol synthesis require insulin, tag synthesis require insulin, but which genesis does not require insulin? Ketogenesis, very good. Please know that. But all genesis require, one is universal requirement of all genesis. Genesis cannot happen without ATP. Without ATP. But some genesis require, most genesis require insulin. Some genesis also require NADPH. Acetyl-CoA is always a source of carbon. NADPH is a source of hydrogen. First fatty acid to be formed is a 16-carbon fatty acid with no double bond. How carbs are killers. First of all, understand that well-fed state is not just high insulin. After a while, well-fed state becomes high insulin as well as high ATP. So tell me, when the body is in a high insulin and high ATP state, what does body want to switch from catabolism to? When the body is in a high insulin and high ATP state, high insulin as well as high ATP anabolism. That's why carbs are killer. Look at this. You eat carb, you turn on glycolysis and TCA, and then you accumulate. You turn on glycolysis and TCA, and you accumulate a lot of ATP. And because of that, what will be inhibited? Your dehydrogenases will be inhibited. What will they back up in the cytosol? What will they back up if dehydrogenases are inhibited? What will they back up in the cytosol? What will be backed up in the cytosol? Citrate, and that's why citrate is a big turn on for fatty acid synthesis. So if I ask you, what can turn on fatty acid synthesis? Do you think it's insulin, ATP, citrate? Are all these three turning on insulin? ATP, insulin, and citrate. Do you relate them to turn on fatty acid synthesis? Know that. And then it starts fatty acid synthesis. But remember, as I told in my lecture, that when you are in a high insulin, high ATP state, especially high ATP, there is a backup, but you still need a forward flow. Then who comes in to overcome ATP inhibition on this pathway in a high insulin and high ATP state? It is fructose, insulin fructose 2,6 bisphosphate. This regulation overrides ATP inhibition on these pathways just in liver to increase citrate in the cytosol. The key is citrate has to be more and more in the cytosol to start fatty acid synthesis. That's why carbs are killer. Why? Do carbs in high do carb burning and high insulin and high ATP state turn on fatty acid synthesis through which intermediate? Which intermediate they turn on fatty acid synthesis? That's why we say carbs are killer. What intermediate turns on fatty acid synthesis when you burn carb? Citrate, right? Citrate turns on fatty acid synthesis. Yes, you burn carb, you turn on glycolysis, TCA. You are in a high insulin, high ATP state. Dehydrogenases will be inhibited and citrate backs up. So citrate is a big time turn on for fatty acid synthesis. But fatty acid synthesis just does not require citrate giving acetyl-CoA. There are other enzymes too. Why? Why do you need so many enzymes? Because how many carbon is acetyl-CoA? How many carbon is acetyl-CoA? How many carbon is acetyl-CoA? 2. And does ACC form malonyl-CoA? Does ACC form malonyl-CoA? Yes. How many carbon is malonyl-CoA then? 3, but imagine 2 acetyl-CoA, 3 malonyl-CoA. But we got to form a 16 carbon fatty acid. That's why we need additional enzyme. So first of all, if you want to do well on the test, keep the right enzyme in the right pathway. If I ask you enzyme for fatty acid synthesis, you will tell me citrate lyase, which is giving acetyl-CoA. Yes. ACC, FAS. But remember, you don't just need 16 carbon fatty acids. So how many fatty acids you know? So you should know carbon length. More than 20 are known as. More than 20. More than 20 are known as. More than 20 carbon. Fatty acids are known as very long. More than 12, long. Less than 12, short and medium. Yes, less than 12, short and medium. You should know carbon length. Very long, 20. Long, more than 12. Short and medium, less than 12. So because you have other other fatty acids chain length in your body, so you'll need an elongase and desaturase. Can you add double bond beyond position 9? Can you add double bond beyond position 9 in your body? No, that's why you have some essential fatty acid which you cannot synthesize in your body and have to be supplied in the diet. So this is all about fatty acid synthesis. First, understand the state, the compartmentalization, site, rate limiting enzyme, regulation. ACC is rate limiting enzyme. Now, who will tell me is FAS rate limiting? That fatty acid synthase complex which is required, is it rate limiting? Long chain is more than 12. Yes. Long chain is more than 12. Short and mediums are less than 12 carbon. Short and medium are less than 12 carbon. Great. So what was I asking you? Oh my God. Anyways, that's what I think I was answering other questions in the chat. What was my question? Yes, is fast rate limiting? Great, I'm getting old now. So it's so yes, very good. So there's citrate lyase, there ACC, there is FAS, there is elongase desaturase. Is FAS rate limiting? Is FAS rate limiting? No. But is FAS regulated? Yes. FAS should be induced by which hormone? Tell me. Which hormone can induce FAS and should induce FAS? Which hormone? Insulin. Very good. So I'm glad you know that it's a well-fed state pathway, overall picture. Remember, you have only 18 questions, so I'm trying to touch important points. But see, when I come back in the interactive session, I will be more focused. But let's first understand everything right now, right? All carboxylases require which vitamin? Please do not forget vitamin in this CP2 exam 2. All carboxylases require biotin. So which carboxylase here is requiring biotin? Acetyl-CoA carboxylase. Is there, should you know biotin? Absolutely. Why not? You should know all your vitamins. So understand you have to make acetyl-CoA available in the cytosol. Then you need the rate limiting enzyme. Then you have FAS to complete fatty acids of 16 carbon. Then you need elongase and desaturase. ACC is the rate limiting enzyme. Do it well, please. It requires which vitamin? Biotin. So are you aware of all these carboxylase? Tell me, where is acetyl-CoA carboxylase used? So when they test you on the enzyme related to the pathway, so where is acetyl-CoA carboxylase used? Which pathway would you relate to? So always, whenever they test you on the enzyme related to the pathway, yes, acetyl-CoA carboxylase is used for fatty acid synthesis. Don't flip-flop. It's not for fatty acid oxidation, right? But where is propenyl-CoA carboxylase if you have read your lectures? At least you should know these two carboxylase. Pyruvate carboxylase is gone. Bygones are bygones, right? So tell me, where have you learned this carboxylase? Anyone can tell me? Propenyl-CoA carboxylase. Anyone, if you have watched your lectures. Propenyl-CoA carboxylase. Anyone? What pathway will you relate this enzyme to? Okay, I'll give you a hint. Oxidation of even chain fatty acid or oxidation of odd chain? Very good. Somebody said that. Oxidation of odd chain fatty acid, you relate this enzyme. So that means you should know oxidation of odd chain fatty acid? Absolutely. Very good if you know that. So do you know these two carboxylase? Absolutely. You know it now, and it requires biotin. Please do not memorize the enzyme in this complex. Just understand that fatty acid synthase complex essential to synthesize the 16 carbon fatty acid. So is this the enzyme for fatty acid synthesis? Absolutely. Put the right enzyme in the right pathway so you know that which enzyme will be active in well-fed state, and don't flip-flop them. Somebody said a memory glands. Now, one thing is knowing your right enzyme. So tell me, is thiolase or thioesterase? Which one is for fatty acid synthesis? Thioesterase or thiolase? Thioesterase or thiolase? Which one is for fatty acid synthesis? Thioesterase or thiolase? And what does it do? Thioesterase is the thiolase is in ketone metabolism. Thioesterase. What does thioesterase do? Once fatty acid is formed, it just chips off fatty acid. The only significance when somebody said that lactating mammary gland have fatty acid, they have short chain fatty acids. So thioesterase, they chip off short chain fatty acids for lactating mammary gland. That's one thing, because somebody also answered that the site of fatty acid synthesis is lactating mammary gland. So this is all is fatty acid synthesis. You push citrate in the cytosol. You need this lyase. But what are the rate limiting enzyme? ACC. FAS is regulating. You need elongase and desaturase just to elongate the length and then add the double bond. Now, who will tell me what is malic enzyme doing here? Sorry, malic enzyme. What is this a source of? So who's the source of? So let's start compiling fatty acid synthesis. Do you need insulin? Yes. ATP? Yes. NADPH? Yes. Acetyl-CoA? Yes. Am I missing anything? I don't think so, which I don't, but anyways, I may. So tell me, what's the source of NADPH for fatty acid synthesis? What could be sources of NADPH? Any pathway you think of could be source of NADPH in fatty acid synthesis? Pentose phosphate pathway. That's why pentose phosphate pathway is involved in reductive synthesis, if you remember. Any synthesis that require hydrogen. One of them is fatty acid synthesis. Cholesterol synthesis. They both require NADF, NADPH from HMP shunt. But there is one more minor source of NADPH, which is malic enzyme. If you see them in your lecture slide, don't panic. It's a minor source of NADPH. So are you aware of all these three enzymes? Are they involved in fatty acid synthesis, which is rate limiting? ACC. Is ACC a well-fed state pathway? Absolutely. Now, ACC is active and polymerized. So tell me, what can polymerize ACC? ACC is active when polymerized. So tell me, what can polymerize ACC? What factors? Insulin, high insulin. What else? What else can polymerize and activate ACC? That just insulin? Citrate, very good. Citrate, what else? Add one more. Citrate, yes, citrate is a ATP. Biotin, I like that. Absolutely good. Yes, you can't miss that. So insulin, citrate, ATP, biotin, they all are very essential for fatty acid synthesis. So don't forget them, right? So now you know fatty acid synthesis, you know it's a well-fed state pathway, you know what all it requires. Now tell me, insulin. So now don't forget that insulin acts by phosphorylation or dephosphorylation. What does insulin does? Always phosphorylates or always dephosphorylates the key enzyme? Phosphorylase or dephosphorylates the key enzyme. So ACC, is it supported by insulin? Is ACC supported by insulin? Yes or no? Which form it will be active? Phosphorylated or dephosphorylated? Which form will it be active? Dephosphorylated. That's all you need to know when you say insulin, right? So now you know fatty acid synthesis, you know palmitic acid is the first fatty acid, but you need to elongate, add double bond. And since you can't add double bond beyond position 9, these two fatty acid becomes essential. So why arachidonic acid is not essential? Why arachidonic acid is not essential? I hope you're following my pace. Is it helping? Are you following my pace, everyone? So tell me which linoleic and linolenic acid are essential. Why arachidonic acid is not essential? Because which fatty acid forms? Very good. Because linoleic acid forms arachidonic acid in your body. And does arachidonic acid form anything else which we are learning in, which we will learn in next week? Is arachidonic acid forming anything that we will learn next week? Any lecture? Arachidonic acid? Arachidonic acid. Yes, it's omega-6. I want to tell you that too. It forms eicosanoids. Yes, prostaglandins, thromboxane, leukotrienes, all the eicosanoids are formed by arachidonic acid. So it's like this: linoleic arachidonic acid, eicosanoids. Linoleic arachidonic eicosanoids. Absolutely. I like that answer. But yes, if somebody is saying they're omega-3, omega-6, absolutely. Omega-3 is linolenic, omega-6 is linoleic and arachidonic acid. Sorry, omega-3 is linolenic, omega-6 is linoleic and arachidonic acid. What is omega-3? Linolenic. What is omega-6? Linoleic and arachidonic acid. EPA and DHA are also omega-3. Now, tag. Many students struggle with tag. All you need to do with tag is what two intermediates, what is tag made up of? All you got to do is what is tag made up of? What is tag made up of? What is tag made up of? Glycerol and fatty acid. But just know that just like for activation of carb, what do you add? What do you add to activate a carb? What do you add to activate a carb? Phosphate. So similarly, what would you add to activate glycerol? Phosphate. So it's not glycerol, it's glycerol 3-phosphate. No, UDP is a carrier. To activate glycerol, you also need a phosphate. So it's when you say that tags require glycerol and fatty acid, please don't forget the activation. It's glycerol 3-phosphate. And how do you activate a fat? How do you activate a fat? What do you add? You don't add phosphate. What do you activate to activate a fat? What do you add? Anyone? Which comes from vitamin B5. No, citrate is activating fatty acid synthesis. I'm asking tags, you need glycerol 3-phosphate. Tag, you need glycerol and fatty acid, right? Glycerol is activated as glycerol 3-phosphate. How do you activate fat? By adding what? What do you do to activate fat? Anyone? Just like to activate carb, you need phosphate. What do you need to activate fat? Coenzyme A that comes from vitamin B5. So that is why if somebody asks you what are the ingredients of tags, it is fatty acyl CoA and glycerol 3-phosphate. The only difference is you got to collect the sources of each one of them. So where do you see tags stored? Major. You see it in muscle too, but I want major. Major tag stores. Where do you talk about tags? Liver and adipose tissue, liver and adipose tissue. So you got to compare, contrast that what is the source of tag synthesis in liver versus adipose tissue. So tell me that in liver, what's the source of glycerol 3-phosphate? What's the source of glycerol 3-phosphate in liver? How can you get glycerol 3-phosphate in the liver? DHAP, very good, which you will get from glucose, glycolysis, and glycerol kinase. I like that. Very good. So how do you get glycerol 3-phosphate from two sources in liver? Glycerol kinase and DHAP. But what happens in adipose tissue? This is liver. In liver, DHAP and glycerol kinase will give you glycerol 3-phosphate. Very good. In adipose tissue, it's only DHAP. Now let's go to the other ingredient, which is fatty acyl-CoA. Who will give fatty acyl-CoA in liver? Who's the major source of fatty acyl-CoA in the liver? So you got to bring in the ingredients, but also know where are the sources you have to get them. So where will you get fatty acids in the liver? Which pathway will give you de novo lipogenesis? But see, in adipose, that de novo lipogenesis is very low. That is why what changes in adipose tissue is the source of fatty acids. So this is what I'm trying to tell you. What's the difference between tag synthesis in the liver versus adipose tissue? So do you know these two are the ingredients first? Yes. Who is giving glycerol 3-phosphate here? Both DHAP and glycerol kinase. But who is giving fatty acid here? Your de novo lipogenesis. So if de novo lipogenesis is minor in the adipose tissue, sorry for the shape of the adipose tissue, right? This is how I could represent that. So if the DNL is very low in the adipose tissue, what is the source of fatty acid to form tags in adipose tissue? Who will bring fatty acid? Who will bring fatty acid to form tag? Chylomicron and chylomicron and VLDL, which is coming right after meals, which is in postprandial after meal. Chylomicron and post-absorptive VLDL. Please see that after fasting, chylomicron will never be high in circulation. What will be high after fasting? It cannot be chylomicron, it will be VLDL, right? So right after meal, who brings in fatty acid here? Chylomicron. Post-absorptive state, VLDL. But do you need an enzyme to digest these tags in each one of them? Do you need an enzyme? Do you need an enzyme to digest tags in each one of them? What's the enzyme here? What's the enzyme here? Should you know that enzyme? Very well. Lipoprotein lipase. Anything that ends with the suffix lipase digests tags. So there is a lipoprotein lipase. Is there any other lipase that you should also know? Apart from lipoprotein lipase, is there any other lipase you should know? Apart from lipoprotein lipase, is there any other lipase you should know? Hormone sensitive lipase. So tell me, lipoprotein, very good, hormone sensitive lipase. Lipoprotein lipase digests tags, hormone sensitive lipase also digests tags. But which lipase digests tags in the adipose tissue or degrade tags in the adipose tissue? Lipoprotein lipase or hormone sensitive lipase? Which lipase degrades tags in the adipose tissue? Lipoprotein lipase, hormone sensitive lipase. First of all, know the difference. Secondly, which one is the well-fed state lipase? Lipoprotein lipase or hormone sensitive lipase? Which one is a well-fed state enzyme? Lipoprotein lipase or hormone sensitive lipase? Lipoprotein lipase, not hormone sensitive lipase too, please. Because hormone sensitive lipase is digesting tags where? In the adipose tissue. Is that tag lipolysis? Is that tag lipolysis? When they test you on the enzyme connected to the pathway. So HSL is enzyme for which pathway? HSL. HSL should be enzyme for which pathway? Tag synthesis or tag lipolysis? HSL. It should be for tag synthesis or tag lipolysis. Tag lipolysis. Is tag lipolysis a well-fed state pathway? Is tag lipolysis well-fed state? No. So HSL is not active in well-fed state. LPL is active active in a well-fed state. HSL is inactive in a well-fed state. Please know the difference between these two enzymes well, right? HSL and LPL. LPL is working here. So do you understand the difference between tag synthesis in liver versus adipose now? Phospholipids can also form tags, minor. Let's do now fatty acid oxidation. Please, please, and please stick to your learning objective, but do not start fat fat metabolism in a low insulin state without turning on HSL. This is the first thing you should do. If you don't make that connection, you will go wrong. So when you talk about fat metabolism in a low insulin state, what is turned on first? TAG lipolysis or HSL. Then everything starts. So should you compare TAG synthesis with TAG lipolysis? Absolutely. So which one is a low insulin state? TAG synthesis or TAG lipolysis? LPL is after meal. Absolutely. LPL is a well-fed state enzyme. Yes. Compare and contrast TAG synthesis versus TAG lipolysis. Which one is a low insulin pathway? TAG synthesis or TAG lipolysis? Lysis. What is the major enzyme for tag lipolysis? Which enzyme digests tags in the adipose tissue? HSL. So know the key enzyme, know the key pathway, know the state, right? Secondly, students are confused between these two things. Fatty acids high in the circulation is different. Tags high in the circulation is different. They are not the same. High fatty acid in the circulation is different from high tags in the circulation. I will tell you the difference in the end. Secondly, tags in the circulation high is different from high tags in the tissue. Where did I say tags accumulate in the tissue? Any condition where tags accumulate in the tissue and cause fatty liver? Tags accumulate in the tissue and cause fatty liver? Alcoholism. That is different from tag accumulating in the circulation. Also, that is different from fatty acid accumulating in the circulation. I will tell you why. So do you know tag stores now? So do you need to eat carbs to form fatty acid and then tag? Are you aware of tag synthesis now? Yes? Yes or no? So do you know tag synthesis? Tag synthesis, you first have to do de novo lipogenesis, then you do tag stores. Where do you compare and contrast tag? Liver versus adipose. So do you identify that correctly? Tag lipolysis is right side. It's a low insulin pathway. But please, whenever they say low insulin, relate to antagonist hormone. So tell me which are the major hormone that will turn on HSL. High and turn on HSL, major hormone. High and turn on HSL. Which hormones when high will turn on HSL? Because low insulin is not enough. Cortisol and epinephrine. First should come to your mind is epinephrine, please. Then cortisol, no glucagon. Just like muscle, you don't talk about glucagon. Adipose tissue, you don't talk much about glucagon. It should be first epinephrine. Nobody said that. So please don't flip-flop the order. When I'm saying adipose tissue lipolysis, low insulin, epinephrine, yes. It should be first high epinephrine, then cortisol. High epinephrine and cortisol. So tell me out of epinephrine and cortisol, which one will phosphorylate HCl? Epinephrine or cortisol? Which one will phosphorylate HSL, sorry? Epinephrine or cortisol, they both turn on HSL, right? Which one of them will phosphorylate HSL? Epinephrine or cortisol? Epinephrine through pKa. So see, you're connecting your signal transduction here too. So what will cortisol do? Epinephrine will phosphorylate HSL and make it active or inactive? Epinephrine should phosphorylate HSL and make it active or inactive? Epinephrine active. So how can cortisol activate HSL? What mechanism it will do? Induction. Because cortisol acts at the level of gene. it will induce HSL, right? So you relate HSL to tag lipolysis, but please, please, and please do not start fat metabolism in a low insulin state without turning on HSL. So in low insulin state, when you turn on tag lipolysis, what is released in the circulation? Glycerol and fatty acid. So this is what I was telling you. So tell me which hormone, when very active, fatty acid will be high in the circulation. Looking at this diagram, which enzyme active leads to high fatty acid in the circulation? Which enzyme active will lead to fatty acid high in the circulation? Which enzyme, when active, will lead to high fatty acid in the circulation? Any HSL, do you understand that? So there's a difference in fatty acid high in the circulation versus tags. HSL, when turned on, when this tap is turned on, fatty acid is high in the circulation. Now, where it will be picked up by liver and muscle. Fatty acid and glycerol will be picked up by liver and muscle. So are you aware of tag lipolysis? Major enzyme HSL. It's low insulin pathway, but you don't stop there. What are the antagonist hormone here for HSL? What are the major antagonist hormone that activate them? What are the major hormones that activate HSL? Low insulin is there, but low insulin is not enough. What is high? Epinephrine and cortisol. So you know that. Now, once fatty acids and glycerol is released, where are they picked up? By muscle and adipose tissue. Please first know normal to know abnormal, because Dr. Panini has a lot of disorders. You know normal, you will understand abnormal. So they are picked up by muscle and liver. Now tell me, if fatty acids are picked up by liver and muscle and it's a low insulin glucagon, somebody has said glucagon for HSL. Please don't talk about glucagon in HSL or adipose tissue. HSL should be epinephrine and cortisol, please, rather than glucagon. Okay. So now tell me, when fatty acid is picked by liver and muscle, it's a low insulin state. What will fatty acid go into? Fatty acid synthesis or oxidation? Because this is all low insulin, right? Your tag lipolysis is on, fatty acids and glycerol is released. They are picked up by liver and muscle. So what is the fate of fatty acid when you are in a low insulin state? Oxidation. And what does fat oxidation give you? Lot of acetyl-CoA and ATP. And what do they turn on? They turn on two pathways in your body, gluconeogenesis and ketogenesis. Please know very well. To increase gluconeogenesis and for gluconeogenesis and ketogenesis in the liver, the prerequisite is the fat should burn. The fat should burn, otherwise these two pathways will not be turned on. But look at this. Is muscle a source of glucose? Is muscle a source of glucose? No, that's why when fat goes into the muscle, what do they give? What is their fat burning there will give you only not glucose, but just ATP. So that is why I know that ATP, exactly. So start fat metabolism in low insulin state by activating HSL. You cannot start fat metabolism without tag lipolysis. Fatty acid and glycerol may be picked by liver and adipose tissue. Please know that fat burning gives you acetyl-CoA and ATP, but only in the liver. Which two pathways are also turned on by fat burning? Gluconeogenesis and ketogenesis. We will do disorder. Let me just finish disorder with it. We will do the rest tomorrow, right? But is muscle a source of glucose? No, fat is burnt in the muscle just to give ATP. Should you know these two difference? Absolutely, very well. I will do MCAT deficiency, diabetes, carnitine deficiency, all are related to this fact. So understand that for fat metabolism in low insulin state, do not forget to turn on tag lipolysis and then talk about fatty acid oxidation, right? So do fat burning and carb burning both give you acetyl-CoA and ATP? Do fat burning and carb burning both give you acetyl-CoA and ATP? Do burning carb as well as fat give you acetyl-CoA and ATP? Yes or no? Which one is in a low insulin state? Where do you get acetyl-CoA and ATP, from burning fat or burning in a low insulin state? In a low insulin state, how do you get acetyl-CoA and ATP? By burning fat or burning carbs? In a low insulin state, how do you get acetyl-CoA and ATP? By burning fat or by burning carbs? In low insulin state. In burning fat, please know that very well. But fat burning supports these two pathways. It's absolutely very important. I'll tell you when I'll do disorders. So let me finish this section. But muscle is not a source of glucose or ketones. Now, who will tell me, this is also very important, does liver form ketone bodies? Is liver site of ketone bodies? Does liver form ketone bodies? Yes, but do liver utilize ketone bodies? Do they utilize ketone bodies? No, please know that fact very well. Liver forms ketone body but does not utilize it. What are ketone bodies utilized by? Extrahepatic tissue. Which one? Very good. Brain and which extrahepatic tissue utilize ketone bodies? Brain and muscle. Brain and muscle. So understand fat burning also is one mistake students make is tag is major in adipose tissue, but you also see tags where in liver as well as muscle. You see tags in liver as well as muscle. So they can also be mobilized, not just adipose tissue. Even liver and muscle tags can be mobilized to give you fatty acid for burning. So don't just relate tags to adipose tissue. It's in the liver as well as muscle, right? So let's do beta oxidation. Let me finish beta oxidation. This will be my last segment. So again, welfare or low insulin, purely mitochondrial. That's why mature RBC can use fat as energy. Can mature RBC use fat as energy? Can mature RBC use fat as energy? No, because they lack mitochondria. Can brain use fatty acid for energy? Can brain use fatty acid for energy? No. Why? CSF does not allow long chain fatty acid. It's not permeable to long chain fatty acid. Is this pathway for energy? Is this pathway for energy? Is this pathway giving you energy? Fatty acid oxidation. So what will turn on this pathway? High ATP or a high AMP? What will turn on this pathway? High ATP, high AMP. So see, it's exactly opposite of fatty acid synthesis. Synthesis need ATP and fat oxidation give ATP. Rate limiting enzyme, CPT1. Yes, it's a low insulin pathway. I will tell you the activators and inhibitors later, but tell me, malonyl-CoA is an activator or inhibitor of CPT1? CPT1 rate limiting enzyme, but malonyl-CoA is an activator or an inhibitor of CPT1? Malonyl-CoA is an activator or inhibitor of CPT1. Activator or inhibitor? Inhibitor of CPT1. You know why? Because where is fatty acid synthesis? Cytosol or mitochondria? When you're memorizing, that's why you don't come to the answer. Fatty acid synthesis is in the cytosol. Does fatty acid synthesis require malonyl-CoA? Does fatty acid synthesis require malonyl-CoA? So if there is too much malonyl-CoA in the cytosol, what does it want to complete? What will it want to complete? Fatty acid synthesis or fatty acid oxidation? Fatty acid synthesis. Now, can these two cycles go hand in hand? It will be futile. So that is why high malonyl-CoA wants to finish fatty acid synthesis, and it's an inhibitor of fatty acid. What? Oxidation. Yes, when malonyl-CoA is high in the cytosol, absolutely right. It inhibits the rate-limiting enzyme for fatty acid oxidation, which is CPT1, because you have to understand synthesis and oxidation cannot go at the same time. If malonyl-CoA is high in the cytosol, it wants to complete which pathway? Malonyl-CoA wants to complete which pathway? Synthesis or oxidation? Synthesis. So what it will inhibit? Oxidation. And what's the rate limiting enzyme for oxidation? CPT1, right? This pathway gives you energy, will do disorder of fatty acid oxidation. Please, you should know chain length and types. Major oxidation, let me just finish oxidation, then I think I'll wrap up. Major oxidation is beta or long chain. Okay, I'll just tell you here. Very long chain is peroxisome. Please note all these points. You got to know normal to know abnormal. Major oxidation, beta or long. Peroxisome is for very long. Very long means more than? Very long means more than 20. Great. Alpha is for branch chain, like phytanic acid. Alpha is branch chain like phytanic acid. Alpha requires an additional enzyme known as hydroxylase. Who will tell me hydroxylase defect is which disease or disorder in Panini's lecture? Dr. Panini's lecture, hydroxylase deficiency is which disorder? So alpha is for phytanic acid, needs an hydroxylase. Have you heard about Refsum's disease? Did he talk about Refsum's disease? Yes or no? Refsum's disease. Did Dr. Panini talk about Refsum disease? Refsum's disease is because of hydroxylase deficiency when which oxidation is missing? Alpha. Alpha requires a hydroxylase. What is omega? I will tell you what is omega. Omega is always turned on when the major fatty acid is missing. So which is the major fatty acid oxidation out of all these? Which is the major? Which is the major oxidation? Alpha, beta, omega, or peroxisomes? Which is the major oxidation? Alpha, beta, beta. When beta is missing, omega increases, but omega is for short chain. I will tell you how. So beta, major, long chain. Peroxisome, very long chain. Alpha, branch chain, like phytanic. Omega, short chain. Omega is always turned on when beta is missing. Does that make sense? Right? So, and according to carbon, second carbon is alpha, third is beta, and omega is the last one. According to chain length, more than 20, very long. More than 12, long. Less than 12, short and medium. So just know where they are used, but please don't get lost in the steps. Just know overall. First of all, fatty acid oxidation is well fed or low insulin? Fatty acid oxidation is well fed or low insulin? Low insulin, absolutely. How many types? Beta, alpha, omega, peroxisome. What are the steps? First, you activate fatty acid in the cytosol. Did I tell you to activate fatty acid? What do you need to add? Look at the cursor here. To activate fatty acid, what do you need to add? Let me bring my laser pointer. To activate fatty acid, you need a CoA. Then you push this with the help of carnitine shuttle. So tell me what else carnitine has. What all carnitine shuttle has? Carnitine as a carrier, CPT1 outer, CP22 inner, and then there's acyl transferase. So these are the components of carnitine. So why do you need carnitine? Why do you need carnitine? Why do you need carnitine in fatty acid oxidation? Because your inner mitochondrial membrane is impermeable to CoA. You have with the carnitine, you have to push fatty acid inside the mitochondria without a CoA. CoA is added later. Yes, to shuttle fatty acid into the mitochondria without a CoA, you need a carnitine. But what does carnitine shuttle have? Carnitine as a carrier, CPT1 outer, CPT2 inner. There's another acyl transferase, and that's all, right? CPT1, CPT2, carnitine as a carrier, and acyl transferase. But once fatty acid is inside the mitochondria, which is the major enzyme here, just like CPT1 is the major regulatory enzyme, but which is the major enzyme which does oxidation? Anyone? Which is the major enzyme that does oxidation in your body? You have learned that. What are the major enzymes that do oxidation? Dehydrogenase. So which dehydrogenase works here? Fatty acyl-CoA dehydrogenase. Now this is different for different fatty acid. There's a long chain fatty acyl-CoA dehydrogenase. There's a short, there's a medium. And have you done MCAT deficiency? Is it your CV? Medium chain acyl-CoA dehydrogenase deficiency, that is your CV. So there are different acyl-CoA dehydrogenase. But what will fatty acid oxidation give you? Tell me. What will fat burning give you? Two products. What are the two major products of fat burning? two main products of fat burning? Yes. What will fat burning? Acetyl-CoA as well as ATP. But acetyl-CoA and ATP in the liver are essential. Fat burning in the liver is essential to turn on which two pathways? Fat burning in the liver is essential to turn on which two pathways? Which two pathways? Fat burning is essential to turn ketogenesis as well as gluconeogenesis. But in muscle, fat burning is only for ATP. In muscle, fat burning is only for ATP. It requires 7 steps to give you a lot of energy. You don't need to memorize number, but you know fat are concentrated fuel, right? So if I tell you fatty acid oxidation, will you start with HSL? Yes or no? Will you start with HSL? So let's do fatty acid oxidation enzymes. Keep the right enzyme in the pathway. Yes, you covered CPT disease this block, but I'm going to do that tomorrow. I'll just finish fatty acid oxidation. So will you start with HSL? So first of all, is fatty acid oxidation low insulin? Yes. Is it low insulin pathway? Do you start with HSL? That will give you fatty acid and glycerol picked by liver and muscle. Both places, because it's low insulin, fat will be burned to give you acetyl-CoA and ATP. Acetyl-CoA and ATP will turn on gluconeogenesis and ketogenesis in the liver. In muscle, it's only for energy. Does that make sense? Steps: first, to activate fatty acid, you need a shuttle to push fatty acid without a CoA. You add the CoA and you have one major enzyme known as dehydrogenase. Now, what are the major product? Acetyl-CoA and ATP. What is the major product of fatty acid synthesis? What is the major product of fatty acid synthesis? Major first product of fatty acid synthesis is what? What do you do when you do fatty? The product of fatty acid oxidation is acetyl-CoA and ATP. But what is the product of fatty acid synthesis? Anyone? Which fatty acid? It's a 16 carbon fatty acid. So what is it known as? Palmitic acid. That's the product of fatty acid synthesis. Product of fatty acid oxidation is acetyl-CoA and ATP. So let's do this regulation, then I'll continue tomorrow. You tell me when you are high AMP means, are you in a good energy status or a low energy status? When you are in high AMP, are you in good energy status or low energy status? Right? You are in a low energy status, and actually, calcium and AMP are hormone independent mechanism. This is how they work. They can directly activate or inactivate the enzyme. They are hormone independent mechanism. So AMP through AMP kinase is phosphorylating ACC. Now, what is ACC an enzyme for? Fatty acid synthesis or oxidation? Fatty acid synthesis or oxidation? ACC, fatty acid synthesis. So if in low energy status, you are phosphorylating ACC, will it be active or inactive? Will it be active or inactive? Inactive. Will malonyl-CoA go up or go down? Will malonyl-CoA go up or go down? What will be turned on then? When malonyl-CoA is low in the cytosol, which enzyme will be turned on? Lower CPT1 and starts fatty acid oxidation. So do you understand how malonyl-CoA is an inhibitor of CPT1? Also, when you are in low energy status, do you want ATP? When you are in a low energy status, do you want ATP? So will you turn fatty acid synthesis or fatty acid oxidation? When you are in a low energy status, you want to turn on fatty acid synthesis or oxidation? Oxidation. This is exactly what it is doing. And rest we will do tomorrow. Okay. I hope this helped, and I'm going to share the slides.